Hope my screen is visible to everyone. Can you see my screen? Okay, great. So till now we have seen a lot of components, different components of the convolutional neural network. So in the morning session, like I was talking about this pooling layer. So you know, like what is the purpose of pooling layer? So, and again, we went through one architecture also, the CNN architecture, where we have seen like fully connected convolution layer, pooling layer, activation function. So everything, whatever we have discussed, these all the components were there in that case. Now, one more component is there, which is being used sometime, like while uh, while defining the architecture. And there is purpose of this. So what is the purpose that we'll see? So and that component is called normalization component. It's also called batch normalization. Okay. So let us dive into batch normalization. So first we'll go for like what is the need of this, and then we'll dive into the concept. So the problem is, so whenever you're designing, like at that time when people used to design neural network, so for the few layers, like for the 2 layers, 3 layers, or 4 layers, it is fine. Like you can train it, and your model will be trained in a proper manner, and you can get the proper model for doing the particular task. But since we know that, like if we are going for more number of layers, in some way we are getting advantage because suppose you have very complex function or very complex problem. So in that case, maybe only few layers are not sufficient. So you need a lot of layers, a lot of different type of layers in the neural network uh, for for solving particular type of job or particular type of problem. Okay. So if you are going for deep, so that's why that is called deep neural network, because you are going for multiple, a lot of different type of layers. So when you are designing deep neural network, that network from the top, it is looking like it can solve any type of problem. But the thing is, whenever you have deep network, that is not easy to train because it is having a lot of or huge amount of parameters. And when it is having huge amount of parameters, then you'll be having a lot of different type of challenges. And due to those challenges, in general, when you are dealing with deep neural network, the problem would be the training part. So how to train it? So most of the time you will be failing to train this network in a proper manner. So these all the things were happening at that time, like in the past, like 2015, 13. At that time, it was happening. Even before that, so people used to face this type of problem. So everyone wants to design very deep neural network because because you like for solving a lot of different complex problem. But the problem was that in the similar manner, whatever we have seen, it's very difficult to train very deep network, very deep neural network. And what are the challenges? Why it is happening? So what they have given the justification or interpretation that whenever you are defining different layers. So let us take the CNN layers. Suppose you have a lot of CNN layers. So maybe con 1, con 2, like that, con 3, con up to n, maybe 100. Okay. Or let us take 10 only. Suppose 10, 11, 12, 13, and so on. So whenever you are going to train the neural network, so what we do, first you take the data set. So suppose you are working on some CFAR, suppose let us assume the CFAR data set. So you have 10 classes and you want to train the model for doing the classification. So what is being done? So let me just give you how first thing, like how the data is arranged. So if you see the data, so you'll be having images, image 1, label one, maybe class one, or whatever the class, maybe dog, and like that. Every image is having the corresponding class. And then what we'll do? We'll give images to the neural network, this architecture, and that image in a batch, it will be processed through the different layers, and then finally you'll flatten it and then give to the classifier. Now what we do when we are going to train the when we are going to give the input, we don't give input as it is. Instead, what we do the normalization of the input, because we know that if we give image as it is having high value like 0 to 255. And if I am doing this multiplication multiple times, because in the convolution layer, what is happening? The multiplication is happening, like dot product. So if the value is getting multiplied, larger value is getting multiplied again and again, maybe at the end you will be getting larger value only as a loss. And if you have larger loss, then it will take a lot of time to saturate. Okay. Because if you are starting from very top of the hill, then it may take a lot of time to reach to the ground. But suppose if initially if you get low loss, then maybe suppose you are starting from here. Suppose you got some loss at this point. Suppose lesser loss compared to this. So if you start from here, then it may take lesser time to reach here. So that's why what we generally do, we don't give image as it is. Instead, we do the normalization of the input. So take the input, take the image. You know the range of each value is between 0 to 255. Now normalize it. Normalize it in such a manner so that every value would be between -1 to 1. Okay, or maybe 0 to 1. So we do the normalization to squash all the values between some range, some smaller range, and then we give that to the neural network. So in that manner, what will happen? Your neural network will be having the input which is having small values. Okay. And in that way, maybe that may help you to get lesser loss at the starting, and then finally you have to move towards the loss close to zero. So this is the general practice. So this is like practical aspect. So whenever you are going to do it, you do the normalization of the full data set. So whatever data set, whatever images you have in the data set, you do the normalization of every image, and then you give to the neural network. Okay. This is the general practice. Now, when you are giving to this, your in every layer we have weight. So suppose you have given, like, let us take convolution layer 1. Then we have convolution layer 2. Then we have convolution layer 3, and so on. Okay. Now in the convolution layer, what we have? We have the weights. We have the filter. So maybe we have 3 by 3 filter here. And what is the inside the filter? All the values, all the weights, which is getting multiplied with your input. It's like the filter is getting applied on the image, and for every portion, it will it will be like dot producted, and it will give you the value. And finally, it will be like your filter will be applied in every portion of the image, and it will give you new image, new feature map, and that will be given to the second layer. And again, second layer will take this as an input. It will give you the output feature map from this, just applying the filter, and then again it will be given to the third layer. So in this way, every layer is having weights, and that weight is getting multiplied with your input. Now the thing is, this is one set of values. This is one step or one iteration. So in one iteration, you're having one set of values here, one set of values here, one set of values here. And every this set of values is getting applied on the input, and and finally it is giving the output image or output matrix. Now Suppose this is being done and you got the loss, and then you go back. And now if you go back means like you'll be finding the gradient of loss with respect to every weights here. And then you are going to change the weights of every layer. That's the goal, because suppose you got very high loss, then your goal is to reduce the loss. And for that reducing purpose, what you'll do, you'll go back, you'll find the gradient of the loss with respect to every W, and then you'll change the W using the gradient by applying the optimizer. Okay, either SGD or any variant of the SGD, like Adam or any type of optimizer you'll be using. And now your W is getting changed. So every filter is getting changed. So next time, even for the same set of images, your W is different. And if your W is different, your output would be also different, because W is having different values. So what is happening, if you just carefully see this, every time, like after the updation, your this distribution of the output is getting changed, because one set of one W will give you one type of distribution in the output. Suppose you got the output is it's also some sort of is coming from the distribution. So if your this input is this filter is getting multiplied on the input, getting dot, like you're applying this filter over the image and you are getting the output. So in the first iteration, you would be having one type of distribution here. Now since your W has been changed, next time the same W, the value of the same W has been changed. So now the values of the output will be also changed. And now it might be the case that this is following some other distribution. So what is happening? Every time your W is getting changed, and due to that, your distribution of the output is also getting changed. And this is applicable for every layers also. So suppose from this layer, from the first layer, you have applied the convolution layer, this filter. Now it has given you one set of values. Now if you just see the input, in the input, the distribution, it was your input was following one distribution, and in that what we have done, we tell these all the images that your mean should be 0. Why? Because we have normalized this image between -1 and 1. So now the mean is 0 and the variance would be 1. So -1 this side and 1 this side. So we have somehow fixed the mean and variance of the input. Because why? Because we have normalized the input images. But when you are applying the convolution layer, since you do not have control over the filter, because your filter is getting learned by itself. So your filter can choose arbitrary value. So now whatever we have here, whatever type of distribution we have here, that will be changed across the layers also. So maybe after this layer, when you apply this filter, first filter, this one, this filter will change the distribution, like it will change the mean and variance of the image. Why? Because it is having set of values and you do not have control over these values. So it could be having any type of values here, and that is getting dot product with every region of the image. So whatever output you'll be getting, it might be having different mean and variance. And this is happening for every layer. So what is happening? Every time distribution is getting changed, even across the iteration also and across the layers also. And this might be the problematic thing, because if you are changing a lot of things in the input, since I'm saying that we are your the distribution of the input is changing, that means range of the input is getting changed. So if the every time the range of the input, range of the like whatever output you are getting from every layer, if the range of the output from every layer is getting changed, then this will make the problem even very complex. But when we have similar type of distribution, it is easy for the model to learn it. But if you mix it, if you give different type of distribution again and again, that means your distribution is changing again and again, then that will make the problem more complex. And this was the issue. And this is the issue when you are going for the more number of layers. Because you have more number of weights, in every layer your distribution is getting changed. And that was like the hypothesis was that due to this, you are not able to train large model or large or bigger architecture. Because in the bigger architecture, you have a lot of layers. And if every layer is changing the distribution, then that is the problematic stuff. Okay. This is also called internal covariate shift. So your variance, this that is shifting, that is changing. Every time it is getting changed. So how to solve this problem? So people observe this. Now the thing is like how to solve it. Okay. So the idea that was given here, that was batch normalization. So since we are getting output from every layer, so why not we normalize it? Why not we put it in some range before giving to the next layer? So since I know that I started from mean 0 and variance 1, unit variance. So I'll make this consistent across the layers. So since your first layer, first convolution layer is getting image which is having mean 0 and variance 1, because you have done it, you have normalized the input image in such a manner so that your mean would be 0 and variance would be 1. That means every value would be squashed between -1 to 1. So why not we do the same thing for all other layers? So this was the idea. And what they have done, we have done the normalization in every normalization of the output of every layer. So whatever output you are getting from the particular layer, first you normalize it and then you give to the next layer. So in that manner, next layer will be also seeing the similar type of distribution what we have shown to the previous layer. I'm not talking about that it should be Gaussian or normal. I'm just talking about that mean and variance should be same. Mean and variance mean should be 0 and variance should be 1. Even in the case of Gaussian also, like if you're going with normal distribution, there also your mean is 0 and variance is 1. But so that means like whenever you have Gaussian then or normal, then you'll be having mean 0 and unit variance. But you could be having a lot of different distribution which can also have mean 0 and unit variance. So here we are not enforcing to the Gaussian or normal. Instead, we are just enforcing them to to have a mean 0 and variance 1. That's all. Whatever distribution it is following, we don't care. But whatever distribution it is following, that distribution should be having mean 0 and variance 1. Okay. So what is being done? They do the normalization of. I'll come to the actual formula, but before that, let me just tell how it is happening. So after every layer, like suppose this is the one convolution layer. So your input will be given here. Now you'll get the output from there, and now this output will be normalized. So you normalize this output in such a manner so that the values would be between -1 and 1. That means your mean is 0 and variance is 1. And then you give this thing to the next layer, next convolution layer. And this will happen for every other layers or every other convolution or fully connected layers. So this was the idea. of the batch normalization. And why it is called batch normalization? Because you are working on the batch. Because initially when I told that we also do the normalization of the original images. So here we do the normalization of the every image because we have the full data set. We have the full data set. So that's why you can apply normalization on every image of the data set. But when you are working on the architecture, when we are passing the images through the architecture, at that time you cannot pass all the images. Instead, what we do, we pass one set of images, and that is called batch. Okay. So pass one set of images, and then you will getting the output of every image, and then you normalize it. And after this normalization, you give this thing to the next layer, like next layer. Again, you get the output from the that layer. Again, you normalize it and then give to the next layer. So in that manner, every layer will be getting the normalized input for which mean is 0 and variance is 1. So in this way, problem would be slightly lesser complex compared to the previous. Because in the previous case, we were not enforcing anything on that. And that's why everyone was getting different type of distribution with different mean and different variance. Now let's see. So this was the motivation why we are going for this. Now let's see like how this normalization is being done. So first we'll go for the fully connected. First just see for the fully connected, how it is being done for the fully connected. And then we'll go for the convolution layer. So for the fully connected, uh, so let us assume that we have n images which we are giving at a time to the neural network, and you are getting maybe suppose you are getting this x. This is the x that you are getting from some layer. Okay, and in this is the x like a set of images you are getting as output from maybe from one layer, first layer. Let us assume that you are getting you have given the normalized input to the first layer and you got output, and this output is having n number of samples in that batch, and every batch like every sample is having d-dimensional vector, because you know that in the case of fully connected you have to provide the vector. So every image has been converted into vector and then given to the neural network. So suppose you are getting this as output, n samples, and each sample is having d-dimensional vector. Now I have to do the normalization of it. Now how should I do normalization? So for the normalization, what we do, we normalized every value of this d separately. So like we have n samples and we have d values in the vector. Now just consider the first value of the d and take the first value of the d from every samples. We have total n samples. Take the first value of every take the first value from every sample, and then find the mean of this and the variance of this, and then normalize every value here, so that every value will be coming between that range. Okay. Now in the similar manner, you do for the second value of the d, then third value of the d, and then fourth value of the d, and so on. Okay. And this is also called per channel mean. So this can be seen as a channel. So you can see this d as a d channels. Now how can we interpret that this d is as the d is working as a channel? So let us relate this thing with your convolutional neural network. So in the convolutional neural network, what is your channel? If I just say convolutional neural network, how you define the channel? Who will give you the channel? So in the case of convolutional neural network, your filter will give you the channel. So if you are applying one filter, you are getting one image as output, one feature map as output. Okay. So one filter is giving you one set of values, and one filter is having one set of values, and that is getting applied on the input image, and finally it is giving you one 2D matrix. Similarly, if we take other one another filter, it will give you another image. So in that way, your number of filters, or we can say like every filter is giving you one channel of the output. So whatever number of filters you are applying here, you'll be getting that number of channels in the output. Now let us see the fully connected. How we actually whatever we are learning here, it's not whatever we have seen in the case of convolutional layer, that is not totally different than fully connected. It's also coming from the fully connected only. But in the case of fully connected, thing was slightly different compared to the convolutional neural network. The main thing was that convolutional neural network is having very small size matrix or filter. But in the case of fully connected, we have very large size filter. Now, what can be seen as a filter in the case of fully connected? So in the case of fully connected, if I show you, suppose this is the input and you are multiplying your input with every row of the W. This is the W matrix. So if you are multiplying your input with every vector of this matrix, that is giving you one value. Okay. And every row is giving you distinct value. In other words, I can say like every row is having distinct set of values. So if you correlate it with the convolutional layer, in the case of convolutional layer, every filter is having distinct value. Okay. So every filter is these are the filters. So every filter is having distinct value, and every filter is getting applied on the image and giving you the output matrix. Now, similar to this, in the case of fully connected, every row is having distinct value. So every row can be seen as a one type of filter because it is responsible for giving one type of values. Similar to your filter, your one type of filter is responsible for giving one type of matrix because you are learning one type of information or you are extracting one type of information from the input image. Okay. And since you know that this is a small filter and that's why it is shared across the every portion of the image. But in the case of fully connected, one filter can cover full image. And that's why you're getting only one value as output. So this is also filter, but this is very big filter, which can cover full image because your input is like, it is covering the full input because every row is getting multiplied with your input. So it's like element wise multiplication with your input and getting one output. So this is also working as a filter only, but one filter is fully occupied the image, and that's why you're getting only one value. But in this case, since your filter size is very small, that's why it is not able to fully occupy the image. Because if it is also fully occupied the image, you'll get only one value. It's like dot product. You'll get only one value. But you have chosen your filter size very small. So that's the difference. Okay. So even in the case of fully connected, we have filter only, but we have very large filter. Now, this is one filter and getting multiplied with your, this is one filter and getting multiplied, getting dot product with the input, and you are getting one value here. Similarly, the second row is the second filter, which is getting multiplied with the input and giving you one another value. In this manner, you have n such type of filters. And every filter is giving you one type of output. So every filter is looking the image, and then it's looking for some type of information from the image. Because this 1D vector is the representation of the image only, na? Because you have converted your image into vector. So it's looking full vector, full image, and it's trying to see one type of information from that vector. And then you are giving the output. Okay. So now if you relate it, here in this case, when we were considering the convolutional layer, I was saying the the output of the filter was giving the one channel. It was happening in this case. I was saying like if we were applying this thing, one filter, small filter over the image, it was giving one 2D matrix. And then I'm saying this 2D matrix as a one channel. Now, in the similar manner, in this case also you can define the channel. So in this case, since your filter is covering full image, so you are getting only one value, and that value is for the that channel. So that's why if you are getting d value, d output value from this filter, that means you have applied d number of rows here, and that means you have d number of separate filters. Okay, and every filter is giving you one output. So suppose if you are getting d outputs, after applying this fully connected, you are getting d outputs from one image. Now here you can easily interpret that each output is coming from a, a different or a distinct set of values. Or in other words, I can say like each value is coming from one type of filter. Okay. So in that way, like we have d values. So that means we got d values from d different filters. And each value can be also seen as a channel. Why? Because you can easily correlate with this. So each filter is responsible for giving you one channel. But since it is fully covering the image, that's why you are getting only one value in the channel. And this is happening for the second, third, fourth, fifth, and so on, all the filters of the W. Okay. And now we are going to normalize this output across the channel. So for each channel, we'll find the mean and the variance, and then we normalize the image, normalize the value. Okay. So I have put a lot of time here because it was very crucial to understand this thing, because otherwise you'll not able to appreciate it. Why we are saying channel here. So now thing is very, very simple. So you find the mean of each output. So D, we have D channel for every sample, and for every channel you do the normalization. So you find the mean of that channel, find the variance of that channel. So this is the formula for mean. Just sum all the values and divide by n. Then you variance. This is the formula for the variance. Find it, and then you normalize. This is the normalization formula. The xij minus mu. Subtract the mean from the value and then divide by standard deviation or root of your variance. This is the very standard formula. So in this way, you can do the normalization. So now every value would be normalized, and the range of the value would be the mean and variance of the value would be 0 and uh, okay. So one question is being asked, like, what is eta here? This is very small number. Okay. So in some case, maybe suppose your variance is coming 0, then it will be inconsistent because something divided by 0 will give you infinity. So that's why for that type of case, we are just giving very small number here so that you should not be having that type of inconsistency. So generally we put this eta. Did you get the answer? It's very small number that we generally put here. Now the thing is, every time actually we are enforcing the output to have a mean 0 and variance 1. But it could be very hard constraint because your model has to, like every time, if you're just putting everything, you're just doing the normalization in such a manner so that mean and variance would be 1, 0, and 1. So it will make the even for the model also, it will be very, very hard constraint because you are putting a very hard rules to the model. So again, if you put very hard rule, it might be the case that your model will suffer from this. So why not we should put some, we can say, we give some freedom to model. So that's like where instead of giving mean 0 and unit variance, we just give some freedom so that it can be having like even for the model it will be slightly we can say less hard constraint compared to this zero mean and unit variance. So what we generally do, so this paper came in ICML 2015. So what is being done? Uh, Instead of giving this very hard constraint, like every time making mean zero and this variance one, why not we should give some flexibility? And that flexibility is this gamma and beta factor. Okay, so you do the normalization, do it, but after the normalization, now what I'm saying that you can multiply, you have two parameter. This is the learnable parameter. One is your gamma. Gamma is like a scaling parameter. So I'll scale it a little bit. And then we have shifting parameter. So you can also shift it. So mean, like I'm saying that mean is zero, but I'm allowing the this function to shift it maybe slightly, not exactly zero, but it can shift from zero to maybe one or maybe. So I'm just giving that flexibility to the model. So I'm not enforcing to become mean zero and variance one. Instead, what I'm doing, what I'm trying to tell the model that this is the freedom range. So in this range, you can shift yourself, and even I'm also giving some scale parameter. So even if you have that variance, what I told that you should be having unit variance, but instead of unit variance, I'm giving some scale parameter. So even you can just for this variance, you can multiply your variance with that parameter, and that is your range. So in that way, what I'm trying to do here, I'm just making bigger range compared to the previous range. So in the previous range, I was just giving that you should be having between -1 to 1 only. Your mean should be 0 and variance should be 1. But now I'm just giving slightly bigger range so that even for the model, it will be not that much hard constraint. Okay, so this gamma and beta has been introduced, and this is again the learnable parameter. So your model itself decide like whether I should need it or not. Okay. Or if I need it, then what should be the value of the gamma and what should be the value of the beta. Okay. And once it is being fixed, then just slight modification in the formula. So whatever we have seen before, that remains same. Do it, find the mean, find the variance, normalize it. Now this value would be between -1 and 1. But now whatever value you got, just multiply that value with the scale parameter, that is your gamma, and then you also add the shift parameter, that is your beta, and that would be the value of the output, or you can say the actual value of the that particular output. Okay, so in the previous case, I was just enforcing to this point. Now we have just given some freedom to that, so that it may like it can go up to even bigger range, and that will give some flexibility to the model in the learning process. So this is being done in the during the training time. Now the thing is how how should we do testing? So during training time, you have the batch. You take the batch, normalize it, like take the output of every layer, normalize it, and then multiply with the scale parameter, add the shift parameter, and then whatever output you are getting, give to the next layer. It can be easily done. Suppose you have done it, your model has been trained. Now the thing is how to do testing. How how should we proceed for the testing part? Okay, so maybe I'll just pause. I'll just ask question from you guys. Let me just allow you to speak because this is very interesting part. So training part is clear because we are giving images into the batch in batch. So at a time you are giving 16, 32 images, and then in batch you can do the normalization. Now during testing, there is no, it's not, there's no fixed rule that images should be in batch. Or suppose you have generated the model and you have given that model to the client, and that client, or maybe you have given that model to the users. Now user can give one image at a time also, or user can give a batch of a set of images also. So it depends on the user, because testing time you do not have control over that. Now if you are giving your images in that manner, and how to do the normalization? Can we apply this batch normalization in a similar manner what we have done for the training? Is it possible to do it?
I have one question. Yeah, regarding the badge that you're telling you're converting into mean and variance.
Yeah,
I
yeah.
don't know if
Yeah.
this is very much apt or not. Consider there is a blood. Want to classify if a blood is there or not. And if I just downsize it, means we are creating mean and variance and we are normalizing from -1 to 1 or 0 to 1. So aren't we losing the depth of that image?
No, actually, normalization is not, it's not changing the, we can say, the structure of the image, because you're not changing number of pixels. Instead, what you are doing, you are normalizing every pixel in certain range. So initially it was like between 0 to 255, suppose at the starting, and now you have normalized it like in such a manner so that the range of this value would be between -1 to 1. So again, you can also denormalize it. So this is the function, and this is the, you can have also inverse function. So you are not losing any information, because you have converted into one range to some other range. That's all.
So the filter captures it. That is what you're trying to do. So the filter understands what actually data, what actual pixel I'm trying to pass, or how is it? How the output is right? How do I verify if the output is right depending on the filter that I've provided?
No, output, you are not, like, you cannot access every layer of the architecture. You can only see the result, the output result. So if you are getting good classification score, then you can say like your model is doing good. So that's the only point where you can say like, hey, our model is doing good or bad. Okay. So that is like, so that's what I'm saying, like whatever you are giving to the model, like whatever you are giving to the your architecture, it will learn in such a manner, like every layer will learn in such a manner, so that at the end you will be getting the uh, required output, or the output that you wanted to get. Output means, like, suppose you are doing classification, then you are getting the accurate class. Okay, so in between how it is happening, how this network is learning, that's the responsibilities of the model. But when we went for the multiple, since you have to solve the very complex problem, so for the complex problem, you need a lot of layers. So when we were designing when we are putting the complex, a lot of layers, then what people observe that putting more number of layers, when we are putting more number of layers, your model is not getting trained properly. That means your model is not giving accurate class. It's not properly trained. So most of the time it's getting failed. So that was the observation. And that's why they tried to find out like what is the problem inside the model, why it is not learning properly. And then they found out like, hey, when we are giving the when we are putting giving the image to the initial, like when we have the full architecture, this is the full architecture. When we are giving this image to this, we were doing the normalization of it. But in every layer, because every layer is having weights, and that those set of values are getting applied over this image. So maybe if you are in the first layer, the weights of the first layer are getting applied over this input image, and then your input image is getting transformed into some other type of images, and that image is given to the next layer, and in that manner you are moving towards this, the end of the architecture. Now the thing was, since at this point you have given the focus like, hey, I will be having mean 0 and variance 1. because you have normalized it. You are having the control over this. But the thing is, when you have here, you do not have control over this because weight could be having any set of values. And if your weight is getting multiplied or it's getting applied, your filter is getting applied over the image, it will change the values. It will change the range of the values in the output. And due to that, your distribution will be also changed. Because in this, the distribution was following the mean 0 and variance 1. Now here your distribution will follow different mean and different variance. And due to this issue, like due to this particular thing, your variance was changing a lot of times. And if your variance, not variance, your distribution was changing a lot of times. And if your distribution is getting changed every time, it will be very hard for the model to capture that or capture the features from that. And that's why they observed this thing, and then this idea came into mind, like why not we should normalize the output of the every layer so that at least mean and variance would be same every time. So if the mean and variance is same every time, then at least we are not, it's not giving guarantee that everyone is having the same distribution. But if mean is same and variance is same every time, then at least all those distribution would be similar. And this will happen across the layers also, because every time across the filter, across the iteration also, because after every iteration, even your W is also getting changed. So even this set of values, what we had in the first iteration, like for first batch of the image. Now first batch of image processed through this, got the loss, and then back propagation happened. And during the back propagation, after the back propagation, we have updated the value of every W. Again, your W has been changed. So next time, even for the same image, you will be getting different set of values. Why? Because of your new W. And this is happening across the iteration also. So this was the major problem that they observed, and that due to that they have given this idea like batch normalization. So why not we do normalization after every layer and then give to the next layer, give that particular thing or that as an input to the next layer. Now what was your question? Like yeah, yes. So now did you get the stuff like the motivation?
Yes, yes, I got it.
Huh. Now the thing is, we are doing this normalization while training, and then we are training the model. Now how to do this normalization while testing, because whatever you are doing during training, you have to follow the same steps during testing also. So if during training you are applying the batch normalization, then you have to apply the batch normalization during testing. But then how should we apply it? So during training, you are providing images in the batch. So at a time you are giving fixed set of images like 16 images, 32 images, and then you are finding this, you are doing the normalization. You know that for normalization purpose you need n, that is like number of samples, because your normalization is happening across the images in that batch. Because if I consider first image here, first value here, then you're considering first value of every image, every sample of the output, and then you are normalizing it separately. Then you are going the second value of every sample. You're normalizing it separately. When I'm saying normalizing, that means you are finding the mean and variance of this, and then you are so normalizing every value here with respect to that. Now mean and variance for this also, say for second also you'll be calculating and then normalizing every value of this. So in that manner, you are finding d number of mean and d number of variance. And one set of values will be normalized based on one set of mean and variance, or one mean and variance. So whatever mean and variance you have calculated for this, that will be only used for normalizing each value here. Whatever mean and variance you have calculated for this, that will be used for normalizing these all the values. So now this is fine. Training is very fine, good. You can, there's no issue. You can easily do it. Now what about testing? During testing, you could be having only one image at a time. Because testing means you're just giving your model. Suppose your model is doing good, you have trained your model and give to the client. Now your client is having only one image. Now that client will take that image and will give to the neural network. And since you have enforced this batch normalization, then again, the neural network has to do the batch normalization. Now for one image, suppose you are getting this n into d. Now if you're getting n into d and your n is 1, now what will be the normalization of this image? Now what will be the, how many means you will be calculating here in this case? You have d output. So you have to calculate the mean for every output. So we have d-dimensional vector. So suppose you got, uh, you are providing, and let us assume that you are providing 16 samples at a time. Okay. So these are the 16 samples you are providing. 16 samples. So whenever I'm saying sample, that is image. So you are providing 16 images to the model at a time, and each image is being converted into vector because you know that you are just using fully connected. So fully connected will accept vector. So what you have done, you have converted every image into, flatten every image into vector. So this is first image, the vector of the first image, vector of the second image, vector of the third image, and so on. Okay. Now you applied the fully connected, first fully connected. And what your first fully connected is doing, it is converting every vector, the dimension of the every vector in some other dimension. So suppose you have started from here. Now suppose this initial dimension was 784 of for every image, and you have like total 16 images. So we started from 16 into 784 in a batch, and now this 784 value has been converted into 100. So suppose your first fully connected layer is taking the, is having the dimension 3, this 100 into 784. So it will take the 784 values and it will convert into 100 value. And this will happen for every sample of the batch. So after doing this, after multiplying this W, you got 16 into 100. Now, what I'm telling you that I'll not give this output as it is to the next layer. Instead, I'll be doing the batch normalization of it. And I also told that your batch normalization will be happen for every value separately. So I have 100 values, but I have total 16 samples. Okay. These are the all 16 samples. And this is the first value for every sample. This is the second value for every sample. This is the third value for every sample. This is the fourth value for every sample, and so on. Total, we have 100 values in every sample. Now, for each value, like this index value, you are getting the normalization of this index value separately. So first value, take the first value from every sample and find the mean of this, find the variance of this, and normalize these all the values using that mean and variance. Okay. Now, in the similar manner, you can do this for the second pixel, then third pixel. So for every pixel, every type of pixel, you're doing the normalization separately. Okay. Are you getting this point?
Yes, sir.
Yeah. What I'm trying to tell you, now this is very easy while training because you have n number of images. You are giving 16 images, 32 images at a time. So normalization is happening across the images for each value of the output. Now the thing is, while testing, suppose you have trained this network, you have trained your model using batch normalization. Now you are going to test it for the for a set of images. And suppose your client is giving only one image, then how should, can we do the normalization of that image? Or if you
No,
do the
sir.
normalization, what will happen?
We cannot do the normalization, I think.
So the thing is like we want to test it and we have to follow the same steps. Whatever you have done for the training, we want to do the batch normalization, but there is problem when we have only one images. Or even we could be having only few images, that could be also the problem. So in the case of one image is very, very problematic. Because if I just find the one image, what would be the mean? If I just say like, what is the mean of this? Like for every value you are finding, suppose you have 100 values, this is the one image. And you have given this image to the model. Now you got the output, 100 dimensional output. And now you have to find the mean of every value. Like you have to normalize every value here. So for the normalization purpose, what do you do? You find the mean of this, find the mean of every value, variance of every value. Now what is the mean of this?
The
If I just say you
variance.
like, what will be the mean value for this? Same value
Sir,
only, na?
sir, would it be value itself?
Yeah, value itself only. So whatever value you have here, you're just taking this. You have only one value, divide by one. So that will give you same value. Okay. And what was the variance?
Zero.
Zero. Now if you are going for normalization, what you are doing? This value minus mean and divide by variance. What will happen?
Zero by zero.
Infinite.
Yeah, you got 0 by 0 4. So this is the problem. So that's why if when you have only one image, you cannot handle it. But we have to somehow apply the batch normalization because we have done it for the training. And if you're not doing it for the testing, things will be different. Then your model will be not able to do it properly. So even while testing also you have to do it. Then how to do the batch normalization? Because you have to do it. So the idea is let us take help from the training. So while training, we have calculated all the means variance after every layer. So why not we take the average of those means and variance of the every layer? Okay, and then save it and then use it, these all the values while testing. So after every layer you got mean for like mean vector or mean matrix, whatever you are getting. So you got mean and variance, and you know that you are going to normalize the pixel of the image, pixel of the feature map based on the mean and variance. Okay, so why not we save this mean and variance of every layer, and we also have given the flexibility terms that is your gamma and beta. So again, these two all terms are also there. So we have to remember mean and the variance and gamma and beta factor. So these are the four things that we have to save while training. Okay, but for every iteration, even for the same layer, but suppose this is the convolution first, or maybe let's take fully connected. So in one iteration, you could be having different mean and different variance, like of the output of this first layer. So suppose you are taking the output of the first layer and you are finding the mean and variance of every value, and then you are normalizing it. Now this is for one iteration. But if you go for the next iteration, since your this W has been changed, so your mean and variance would be also changed. And again you find the mean variance and again you normalize the this output. So that it will be coming in range maybe 0 to 1 or maybe some if you're giving some like some flexibility, then you'll be having some gamma and beta factor also. So actually, your mean, even for the same layer, the output of the same layer, your mean is also getting changed across the iteration. So that's why what we'll do? We'll take the average of all the means of the particular layer. Similarly, we'll take the average of all the means and variance of the next layer. And in that way, we'll be doing it for the every layer. And also, we do not take simple mean. It is like running average or running average mean. Or you can say like what we have seen before, no? That time when I was explaining Adam. So we'll give more focus, more attention on the recent one, less attention on the least, or we can say the epoch or the iteration which came very early. Okay. So this is like running average. So we'll find the running mean for like running average for the mean and running average for the variance. And then we'll also save this gamma and beta, running average of gamma and beta, and then we'll save it. And this will save for every layer. Okay. Now you no need to do anything while testing. While testing, whatever you are getting from, suppose you are getting this is the layer, these are the layers. You are giving out input. Maybe your input is given to this. You got the output. Yeah. Now you normalize this output with the help of the mean and the variance of this layer which you have saved while training. So whatever you have like average mean and the average variance and this gamma and beta factor while training, that you have to save and that will be used here for normalizing it. So you no need to find mean and variance again. It's just coming from the training
So,
part.
so
Is
sir,
it
that
clear
will be
to?
overfitting, right? We are dependent on the training data. So basically,
Ah,
whatever image we are providing, we are again going
hmm.
back to the training data, and we are trying to align it with the training data. So
No, after training, once your training is done, because you are this mean and variance, you are taking the running average. So it's like across the iteration, you took the average of this. So while training, you have shown a lot of images to the model. And while testing, again, whatever images you are going to give while testing, those images will be also similar type of images, no? Because it should be having the similar type of classes. Then only you'll be able to then only your model will be able to give the class. It should not be totally different type of images. Suppose you have done classification for the dog or cat. So
So
classification between
obviously,
dog
sir,
and
now
cat. Yeah.
if I provide an image which is aligned
Hmm.
more aligned with the training data, then I am going to get the expected output. But if the
Hmm.
image is not much aligned, and then I'm applying this normalization, which is based on the training data, then
Hmm. Hmm.
then I'm trying to align the image with the training data only. That's like a overfitting case, isn't it? I mean, I'm just trying to understand it
Yeah,
because
in some manner, but actually, this mean and variance is not. It is not. Yeah, it's coming from the image, but it's not coming directly from the image. So you are just mean means you are just fine. It's because it's coming also from the layers. When you are giving input image, so your input image is getting converted or getting changed by the layer. So your layer is involved. Due to layer, your the distribution was getting changed. So everything, whatever is happening, that is happening due to the layer, due to the weight matrix. Because weight matrix is getting it's like changing the distribution of the input. So this whole thing was happening due to the layers. So that's why like in other words I can say like mean and variance, these are like more or less dependent on the layer more than image. Again, I also agree with your point. In some manner, it's also dependent on the training images, but it is also
yeah.
dependent on the layer.
So
So
instead of
maybe
doing that, let's say if we are getting only one image instead of a batch, can we not repeat that image with a minor variation and then convert it into a batch rather than rather than going back to the training
yeah,
average running averages?
yeah, there could be a lot of ideas. Even
Yeah, okay.
whatever I'm explaining here, after this, a lot of different ideas came, and they
Okay,
have given
got it,
even
sir.
better
Thank you.
ideas. So this was the idea which was given in that paper. But whatever you are saying, that can be also done. But again, you also need to see like what are the challenges that will come. Because if you're going with that, maybe you could be having different type of challenges. Okay. So this is now the testing part is very, very easy. So let's do the testing. Fine. Just take the mean and variance, all the things from the training part, and then just apply it. That's it. Okay. So in that manner, you now the calculating this mean and variance. These are like just simple linear operator while testing. While training, you have to calculate it while training, but while testing, you don't need to calculate anything. It's just like you use it from the training part. So it's just linear function that you're doing. So that is we can say that is one more advantage because while testing, you no need to calculate anything. So everything while training, you do it, calculate it every time. But once you are done the training, now this is very simple, very straightforward. Just use it, and that's why like this is just linear function. Just take it, multiply. It's a simple multiplication that you are doing. Multiplication and subtraction and like that. Multiplication, subtraction, and division. That's
Sorry to ask you, sir, again one
it.
question. So again, we are going to linear, right? That y is equal to xj plus beta or
Hmm.
gamma. So it's like from linear we want to have non-linearity. So we are putting activation functions, and now again with
At,
normalization we are making it linear.
but this is happening after the layer. Suppose first layer is having a set of linear function and a set of non-linear function. So suppose you have applied one layer and you got the output, and then you are applying this function. The job of this function is different. Job here is not to put the non-linearity. Instead, the job is to make normalize the output. That's all. The this non-linearity is already done. That is all. So this is just one part of the architecture. It's not your architecture. So don't confuse with the architecture. So we'll come to the architecture. So in the architecture, it will be like one part of that architecture. But we'll be having all the non-linear function, all the activation function, all the convolution layer, all the fully. So everything will be there. But apart from those things, we'll be also having this layer for doing the normalization. But why I have told here because while training you are calculating it, so that is like slightly we can say hectic process. It's like time consuming process because after every layer you are doing the normalization. But when we come to the testing part, then you are not doing any type of you are not finding mean and variance because the most of the time will be given to the calculating mean and variance. But since you are not calculating it, you are just using it from the training. So that's why now this is it's like linear operator because you don't need to calculate it separately. So if this is linear operator, it can be fused anywhere in that layer. Like uh, even you can fuse this thing with the previous layer because linear function you can just take it. So we'll see again. So when we'll be applying a lot of layers. So in between wherever suppose you are applying convolution layer here and maybe after convolution layer you are getting whatever output you are getting, then you are applying this non-linear function, this batch normalization. So this batch normalization you are calculating separately and it was required in the case of training. But when coming to the testing, then this batch normalization is just like you are multiplying or dividing or summing, like or subtracting the values which we have calculated before, like while test training. So here in this case, you are not calculating any mean or variance. So why not we should combine this thing in this because suppose your convolution here and or maybe fully connected here, fully connected, and then you have applied this thing. Now this is fully connected is also linear function. This is also linear function. Then you can combine these two linear function. So this can be done. That this type of things can be done while testing. But while training, you cannot do it because while training, you want output from the layer, and then you have to find the mean and variance, and then you will be normalizing every value there. But while testing, you don't have to find the mean and variance. So that's why you can also combine these two in one. So this they have just given this idea like while testing also we can make this process fast. Now let's go for convolution layer. So in the case of convolution layer, now things are very simple. So I already have told that you are going to normalize your image for every channel separately, and that we have seen in the case of fully connected. And in the case of fully connected, your D was referring as a channel, and that I already have given the interpretation for this why D is channel, and that's why you are finding D number of mean and D number of variance, and then you would be also having d number of gamma and d number of beta. Okay, and then you we have normalized every value of this t with the corresponding mean and variance and beta and gamma. Now, how should I do it for the convolution layer? So in the convolutional layer, you will be having the matrix. Okay. So suppose this is the convolution layer. So I'll be having, suppose you got this output from the convolution layer. So you will be having the n number of samples and you will be having the channel C and then height H with W. Now what I told you that I'll be doing this normalization for every channel separately. So whatever we have done here logically, in a similar manner, we'll be doing this normalization for the convolution layer or output of the convolution layer. So here, since we have C channel, then we are going to normalize every channel separately. So for each channel, you'll be having mean and variance. So in totality, you'll be having C number of mean and C number of variance because for every channel you'll be having separate mean and variance, and for every channel you'll be having separate gamma and beta, and then you'll normalize every channel with the help of the corresponding mean, variance, gamma and beta. So this is the thing how they have done in the paper. This paper came in 2015. This very early paper. Okay, so that time what they have done, they have arranged the architecture in this manner. So what they have done, they have put this batch normalization after every layer. So suppose this is the first layer. Maybe we could be having okay, from this side. So after this FC layer, you can see they have put batch normalization and then they are putting the 10H. Okay. So how it is happening? First you apply the fully connected and then you apply the batch normalization. So whatever output you are getting from the fully connected, then you normalize it and then give to the non-linear function. So what, like when I was explaining it, so what I told that while testing, you can combine these two things. So while testing, you don't need to find the mean and variance for this. And you have seen that this is linear function and FC is also linear function. So while testing, you can combine FC and BN in one. And then you can just give to the 10H. So in this manner, they have designed the architecture. So fully connected, then batch normalization, and then the activation function or nonlinear function. So first we apply all the linear function and then apply the nonlinear function. Again, whatever output you are getting from here, then apply this fully connected, then batch normalization, and then you apply the nonlinear function. So this was the observation. So whenever you have a larger network, you are going to design large network, then if you go with the batch normalization, it will be easier to train. Even with batch normalization, even if you give high learning rate, uh, your convergence will be faster. So, like in most of the cases, even when you are going with high learning rate, then your convergence will be slower. So, but when you have batch normalization, then it allows high learning rate, and with the high learning rate also, it will give you faster convergence. The network become more robust to the initialization. Now, whatever initialization you are giving, whatever initial value you are providing, so like you have to start from somewhere. So whatever values you are giving in the W, it will not affect a lot to the network. Whatever you are giving, like at the end, you will get the robust model using this batch normalization. Okay. So whatever starting point is, no problem. Start from there, and batch normalization will help you to reach to the convergence. This is also act as a regularization because with the help of batch normalization, you are trying like you're getting better model. Okay, more generalized model. So in other words, I can say like this is also acting as a regularization because when I was discussing the regularization, the purpose of the regularization was to reduce the overfitting or underfitting. Okay, and that's why but the main purpose the purpose of the regulation was not to train the model uh, to match with the ground truth, but instead the goal of the regulation was to make the model more generalized. Okay. So here also, this batch normalization is not directly helping you for getting accurate model. Instead, it is trying to make the model more generalized so that it will work better while testing. Okay. Indirectly, it is also happening because indirectly, even if you have regularization, that regularization will also help you in some manner to get the or to like match the like not exactly, but in some manner, it's also helping for getting the robust model, but not directly in indirect manner. But the main purpose is to make the model more generalized. Okay, and also zero head over test time. So you don't need to calculate anything while testing. So these all the things are very good, and they have observed that when we use the batch normalization, it is giving better performance. Now let us come to the cons part. Now whatever I explained here, that's fine. But what people have observed that there are some cons. The first point is it's very difficult to understand this concept theoretically. So whatever I have given hypothesis, whatever I have given justification, these all are coming from the paper. These all are coming from the different researcher. But the proper theoretical understanding is not there. Proper theoretical proof is not there. So this very not well understood theoretically. So very difficult to understand this whole concept theoretically. Another problem is it behaves differently during training and testing. And this is like very common source of bugs. So what I said that hey, if you use batch normalization, it will give you very good model, but that is not guaranteed. So maybe while training, everything is looking very good. Hey, you will be happy. Hey, I got the model. But when you are going for the testing, and suppose you are doing testing, it it might be the case that you are getting very wrong result. As one of you told that since we are using the mean and variance from the training, so it might be like your that mean and variance would be aligned with the training data. And while testing, if suppose things are coming totally different, it may fail. So again, so that's why this batch normalization is also not very good. So if it is doing good, you accept it. Not doing good, you remove it. Okay. So we have a lot of different solutions. So this was like early approach, but later all different type of things came into the picture. And nowadays people don't use this batch normalization. We have like a lot of different things which can be used instead of this batch normalization. Okay, so I'll stop here. So we have done the convolution layer. Now the next part is this uh, CNN architecture. So that we'll see in the next class. Hey, any question? Then please ask. Otherwise, I'll stop.
No, no question, sir.
Okay. Okay. Okay.
Thank you, sir.
Thank you. Thank you.
Thank you, sir. Thank you very much.